let us just take up one more chapter, which of course is equally important for us at JEE level. In recently concluded JEE exam, that is of 2013 also, quite a good number of questions they have given us from this particular chapter. The chapter what I am dealing with is electrostatics, the study of charges which are at rest on the surface of a body. And this particular chapter deals with electric field intensity, electric potential and electric capacity. Along with them, the important most applications of linear charge density, surface charge density and volume charge density as such. So these areas we are going to cover up in this particular chapter, that is electrostatics. Let me just work out few applications taking different model problems over here. Let us take the very first problem of this order. The linear charge density of a thin metallic rod varies with the distance x from one end as lambda is equal to lambda naught x square, where 0 is less than or equal to x, less than or equal to L. That means x lies in between 0 and L. The total charge on the rod is how much? That is a question 1. And of course options are given this way. First option is lambda naught L cube by 3. Second option is lambda naught L cube by 4. Third option is 2 lambda naught L cube by 3. And fourth option is lambda naught L cube by 2. The correct option for this one is the first option, that is A, lambda naught L cube by 3. How come that be the case? Let us work out first of all the linear charge density of a thin metallic rod. According to him, the question 1, when we talk about, there is a rod taken up of length L over here. Out of this particular rod, let us just consider a small element of length dx. If I just consider this being the origin, the distance to this particular element that is considered, I take that one as x. And obviously, the total length to the other end of this rod, that now becomes L over here. So this is actually the concept what I am considering. Instead of taking the entire rod as a single element, like I consider a small element of thickness dx over there, which is at a distance x from one end of the rod. After calculating the value of linear charge density for this element, I used to integrate that one in between the limits 0 and L as such to get the total charge on that particular rod as such. So this is the methodology what I am adopting to just work out this problem. So let us first of all consider what is linear charge density. Linear charge density, that of course is lambda. We people used to write dq by dx as far as this particular element that is concerned. Charge per unit length, that is what we officially call it as linear charge density. Likewise, suppose if I say surface charge density, charge per unit surface area we people used to take up. So in this particular case, we are dealing with linear charge density here. So I can directly write this equation this way now. This now becomes dq is equal to lambda dx. But officially in the problem that lambda value is given to us. What is that lambda? Lambda is given lambda naught into x square. That is the value that has been provided to us in this problem. So I just write that in place of lambda. Lambda naught x square dx. But when I just want q from this, in the sense dq is the small charge that is on that length of the element dx. If I want the total charge on the entire rod, then one should integrate that between the limits 0 and the total length of the rod, which is nothing other than L there. So we now can write this implies charge, which is integral of dq, is now integral between the limits 0 and L lambda naught x square dx. And even in the problem also, it's very clearly mentioned that x lies in between 0 and L. 0 means the beginning of the rod. End point is going to be at a distance L from that particular beginning. So you can say the total length is L over here. So between 0 and L, when I integrate this value, I will be getting the total charge on the entire length of this rod as such. That is the basic concept. So if I take up this integration part of it, lambda naught integral 0 to L x square dx. In fact, we all know that integral x square dx is x cube by 3. So lambda naught x cube by 3 in between the limits 0 and L. Now just substitute the upper limit over there. You will be getting the total charge on that entire length of the rod, that is q, now is going to be lambda naught L cube divided by 3. This is going to be the total charge that is there on the rod as such. I just remind you once again, on the entire rod of length L, since he has given you in the problem, this x is lying in between 0 and L, I am considering this itself is the origin here, that is at 0. And the other end of this rod is at a length L. So to calculate the total charge on the entire length of the rod, we imagine or we consider a small element of length dx over there. That is what I have done. This is of length dx, which is at a distance x from the origin. That is the beginning point of this particular rod. So if I take this distance as x, according to the formula, linear charge density, lambda now becomes dq over dx, and dq now becomes lambda dx, but lambda is given lambda naught x square. Substituting that value and integrating this value between the limits 0 and L, we be getting lambda naught L cube by 3. This particular option, if you look at of all the 4 options mentioned over there, this is in coincidence with the very first option that has been given in the problem. So the key or the answer for this particular question is going to be A over there. Look at that A, the very first option, lambda naught L cube by 3 as such. That is the correct answer for the charge on the entire length of this particular uniform rod of course uniform cross sectional area there. So this is the very first problem what we have in this order. One of the best models for you to remember, particularly questions on linear charge density. Several times they have mentioned and they have asked in the final examination of JEE. Remember that point. Let us switch over to the problem number 2. Let me read it out first. 2 free charges plus q and plus 4q are placed at a separation L. The charge to be placed in between them such that all the charges stay At equilibrium, what is the charge that is to be calculated here? Not alone is that the case, at what distance that charge is to be placed, that also we just have to calculate. So two things he is asking you. What is the magnitude of charge that is to be placed? That's one area. And second point is, at what distance that particular charge, the third charge, is to be placed for the entire system of all the three charges to stay in equilibrium. That is the point. As usual, 4 options are mentioned here. Let me read out those options first. First option says minus 4q by 9 at a distance L by 3 from plus 4q charge. Second option says minus 4q by 9 at a distance 2L by 3 from the charge which is plus 4q. Third option says 4q by 9 at a distance L by 3 from the charge q. Similarly, the fourth option has been given this way, minus 4q by 9 at a distance L by 2 from the charge q. They are the options mentioned. But out of all the 4, the correct option is going to be the second one. So B is the correct answer for this. But let us check first of all, what is the condition for equilibrium of charges in a particular system. Let us start this way. Two free charges plus q and plus 4q are placed at a separation of L. That's what has been mentioned. So if I just show you here, this is the charge q. Exactly at a separation distance of L, there is another charge that has been placed over here as plus 4q. This is the description given in the problem. But what is his question ultimately? Where should another charge, a third charge, that should be placed in between for the system to be in equilibrium? So first and foremost, let us consider this is the charge what we people are keeping it at over there. That q value we have to calculate. One point is that. And secondly, at what distance that is to be placed, that also we just want. So let us check this way first of all. When I consider x is the distance to the point charge q from the capital Q charge, then automatically you can understand L minus x, that now becomes the remaining distance that is between plus 4q charge and this point charge what is taken as plus q. So when you just look at this one, this is the charge that is to be calculated and it is at a distance x from the first charge, that is capital Q, L minus x distance from the second charge, that is plus 4q charge as such. So let us start this way. First of all, this particular charge should be in equilibrium. First and foremost, when I talk about q must be in equilibrium, what is the condition over here? The force between these two and the force between these two are supposed to be equal and opposite. That means what you should understand, the net electrostatic force experienced by the charge small q must be 0. I just repeat the statement once again. The net electrostatic charge that is acting on the net electrostatic force that is acting on the charge small q must be 0. That means you can understand 1 over 4 pi epsilon naught q times small q by x square, that now must be equal to 1 over 4 pi epsilon naught small q into 4 capital Q by L minus x whole square. So this, according to Coulomb's law, we people are just equating the effective force acting on that one to be 0. That means this minus this must be 0. That is algebraic sum of forces must be 0. If I equate these two, I can cancel these two, I can cancel these two, I even cancel these two as well. Take root over here, this becomes 1 by x, this becomes 2 by L minus x. That now gives you L minus x is equal to 2x, or 3x must be equal to L, then x must be L by 3 as such. That is the concept, first of all, you should understand. So at what distance it is to be placed? We people are now getting L by 3 from where? L by 3 from capital Q. But look at the options given first of all. L by 3 from capital Q has been given in the third option. But unless we calculate the magnitude of Q, we cannot come to any conclusion directly there about the options. Now, what is the magnitude of this charge? Let us check this way. For the entire system to be in equilibrium. So what you should remember? For the system to be in equilibrium, for the system to be in equilibrium, what is the condition now? Take any one out of the two charges, calculate the effective force on it, and equate that one to 0. So what must be the condition there? Sigma F must be 0. What do you mean by sigma F over here? Algebraic sum of forces acting on one of the charges out of the three. One of the charges out of these two in particular, that must be 0. So what should we write now? Take this pair first and write down the formula. 1 by 4 pi epsilon naught Q into Q by x square. And what is the second force between this charge and that charge, please? It is plus Q into 4Q by L square. This must be 0. I hope all of you might have followed this particular concept. The force acting on this due to the other two charges I am calculating. In fact, I have calculated these two values. And algebraic sum of those forces must be equal to 0. That is a condition. So what I can write now? This implies Q times small q by x square must be equal to minus Q times 4Q by L square with a negative sign. Of course, I can write that. Q getting cancelled. So what is x already we have calculated? That is L by 3 from the first one. So we can write directly this way. Q by L by 3 whole square is equal to minus 4Q by L square. Just look at the simple calculation here. L by 3 whole square now becomes L square by 9. So automatically this becomes 9 small q is equal to minus 4 capital Q, because L square gets cancelled. What is the value of Q, the question? So Q must be minus 4Q by 9. So what must be the magnitude of this charge Q here? It should be minus 4Q by 9. Fine. So minus 4Q by 9, if you look at in the options, all the four, first option has got that one, second also has got that one, third also has got that one. But the concept is you should club these two and search for the answer. See the second option correctly there. Minus 4Q by 9 should be the magnitude of small charge Q. Fine. And what is the distance he has given in the second option? 2L by 3 from plus 4Q charge. Every one of you can understand when this is the distance x, which is L by 3, then what will be the remaining distance there, please? It is L minus L by 3. Is it not 2L by 3? So you can understand x is L by 3 from plus q means you can even write 2L by 3 from plus 4q charge. Like that also we can remember. So x is equal to L by 3 here means 2L by 3 from the other end. That is the idea. So q must be minus 4q by 9. That should be the magnitude over there. In addition to that, this is the distance from the greater charge out of the two. So which is the correct option over there? The second option is exactly tallying with these two numbers, these two values. So minus 4q by 9 at a distance 2L by 3 from plus 4q charge. That is the correct option for this particular problem. So what will be the correct answer now? Answer is supposed to be the second one. Answer must be B as far as the second question that is concerned. But only thing you should understand here is whenever a system of charges, maybe 2 charges or 3 or even more sometimes, whenever a system of charges are in equilibrium, if that fellow says, then one should understand the algebraic sum of forces acting on one out of the cells, out of all the charges, that should now be 0. The algebraic sum of forces, if you can equate them to 0, whatever the value you require out of that, you can directly get that one. This is one of the best models we have of this particular chapter in the form of problem 2. That is the concept over here. Let us switch over to the next problem, that is problem number 3. Let me read it out once again. An electron of mass me, initially at rest, moves through a certain distance in a uniform electric field in time t1. A proton of mass mp, also initially at rest, takes time t2 to move through an equal distance in the same uniform electric field. Neglecting the effect of gravity, the ratio T2 by T1 is nearly equal to how much? Options are given this way. The first option says it is 1. That means they are equal. T1 and T2 are equal. That's what has been the meaning of it. And second option, root of mass of proton by mass of electron. Third option, root over mass of electron by mass of proton. And fourth option is given 1836. In fact, you all must have got this idea. 1836 is a number which is actually the mass of proton comparing to the mass of an electron. But of course, that's not the correct answer over here. The correct option for this one is the second one. It is root over mass of proton by mass of electron. That is the correct option for us. Firstly, we need to understand what is the force that a charge used to experience whenever it is entering into an external electric field of strength capital E. Let us consider this way. If Q is the charge that is entering into an external electric field of strength E, then you can understand straight away force experienced by the charge will now be F is equal to EQ. That is the concept. So one should understand the force experienced by a charge Q which is entering into an external electric field of strength E. In fact, one should understand here that it should not move along the direction of the field. By any chance, if the charge moves along the direction of the field, then automatically it does not experience any force at all. The force is going to be 0. So here, what is the very meaning of it? the charge is supposed to enter at right angles to the direction of the field. That of course he has not mentioned anything over there as 0 as the answer. So one should understand that this is entering in such a way that it is experiencing some amount of force inside the field as such. That is the concept. So if you take this formula, what is the force experienced by an electron first of all? That you can understand E into the charge on the electron, that is E. Exactly, this is actually the force on an electron. And what else he has given you there? He is asking you to calculate what will now be the acceleration of electron. Acceleration of electron in the field, that we can take it as acceleration of electron, which is force divided by mass. Exactly in the same manner, similarly, acceleration of a proton, when I want to write, that can be rewritten as E into E by mass of proton. In fact, why should we take this acceleration here? He has given a wonderful clue in the problem. Both the electron as well as the proton have traveled the same distance through the field. That's very, very clearly as mentioned. Even the electron is traveling some distance, and proton also is traveling the same distance, but with a different time in the same field. So one should understand, according to this, distance traveled must be half at square according to equations of motion. One of the equation of motion we are taking up here, that is half at square. So S can be written as half of, what is the acceleration of electron now? E by mass of electron into T1 square. That now must be equal to half of E by mass of proton into T2 square. So you can understand the same distance is traveled by both electron as well as proton. You can cut these things over here which are common. And what is his question? You carefully observe. It's not T1 by T2 he is asking. He is asking you the ratio of T2 to T1. So what can we write? This implies T2 by T1. That of course is going to be under root mass of proton by mass of electron. This is the concept you need to understand. This in fact you can take directly from this equation also. Only thing you have to get this idea here is force experienced by both the electron and proton in the same electric field, that remains same and constant. Where the value differs, acceleration will differ, because acceleration is force by mass. That mass of electron and mass of proton, since they are not equal, they will have different accelerations, even though the field is same, even though the distances covered by them in the field also are equal. So these are the points you have to take. T2 by T1 must be equal to root over mass of proton by mass of electron. If you look at all the four options, second option is directly given like this itself. Therefore, we can say the answer for this particular question is the second. In fact, we can take that one as B here. That is the correct option for this problem. This type of a problem also has been asked in previous papers of JEE. Generally, what are the particles they take? Whenever they ask you to calculate the ratio of time periods, ratio of accelerations, like, generally they prefer taking either a proton or a deuteron or a tritium ion or an alpha particle like. So such concepts or such particles are going to be taken up in such this type of a model problem as such. So this is problem number 3 for us in this order. The next problem is problem number 4. 3 concentric metallic spherical shells of radii capital R, 2R and 3R are given charges Q1, Q2 and Q3 respectively. It is found that the surface charge densities on the outer surfaces of the shells are equal. Then the ratio of charges given to them are given to the shells. Q1 is to, Q2 is to, Q3 is how much? Options are given this way. The first option says 1 is to 2 is to 3. Second option 1 is to 3 is to 5. Third option 1 is to 4 is to 9. And fourth option 1 is to 8 is to 18. And the correct option for this particular problem is the second one. So it's 1 is to 3 is to 5. That is what you have to understand. So what are the things he has given? Let me just tell you by considering a small diagram here, the figure. He is just talking about 3 concentric spherical shells. Since they are having the same and common center, first one has got radius R, he said. Second one he has got the radius 2R, he said. Third one he said the radius as 3R. So 3 different circular or spherical shells, one inside the other, having a common center, concentric circular, just spherical shells like, fine. He said charge is given to this one as Q1. For the second one it is given Q2. For the third one it is given Q3. He has given a wonderful clue here. What is that clue? The surface charge densities on the outer surfaces of the shells are equal. Surface charge densities are equal. That is the concept. So what we should understand here out of this? When I take surface charge density, that we represent it as sigma. It is charge by surface area. Generally 4 pi r square we take for a spherical shell. So what is the thing he has given you? Sigma is same for all the 3 shells like, that's what he is talking, over their surfaces. So what you should understand is the effective charge on the second sphere now will be Q1 plus Q2. You better can understand how. If I take the charge on this outer shell as positive Q1, due to induction negative Q1 will be on the inner side of the second shell. Positive Q1 goes to the other side of the second shell. Other side means what? Outer side of the second shell. So what will be the total charge on this one now? Second shell, it should be Q1 plus Q2. Exactly in the same manner, what would be the total charge on the outer shell, that is the third shell on its outer surface I am talking? That again will be Q1 plus Q2 plus Q3. So induction takes place in between. Due to induction, similar charge will be seen on the other side of it. So naturally here will be Q1, here will be Q1 plus Q2, here will be Q1 plus Q2 plus Q3. They are the charges you need to identify first of all. Now you can say, since sigma values are equal on all the 3 shells on their outer surfaces, let us equate them now. First one says it is Q1 by 4 pi r square. What about the second one? It's q1 plus q2 by 4 pi into 2r whole square. What about the third? q1 plus q2 plus q3 by 4 pi into 3r whole square. So you can straight away understand 4 pi r square gets cancelled throughout in the denominator. But here you will be getting 4 left. That means q1 is equal to q1 plus q2 by 4 is equal to q1 plus q2 plus q3 by 9. Now check it carefully. From these two, what will be q2 then? q2 will be 4q1 minus q1. That will now be 3q1. Now take the first one and the third one this time. What is q1 plus q2 officially? It is 4q1. That you write it here. So what can we write? 4q1 plus q3 by 9 is equal to q1. Then what will be this q3 now please? It is 9q1 minus 4q1, which now becomes 5q1 as such. Look at this simplification carefully. You will be getting first charge as q1. There is no change in that value. q2 now in terms of q1 will be 3q1. Exactly like that. q3 in terms of q1 will be 5q1. Then what is the ratio? That is the question that is asked. q1 is to q2 is to q3. Now becomes q1 is to 3q1 is to 5q1, which now can be written as 1 is to 3 is to 5. So what should be the correct ratio of the charges on them? On the outer surfaces, 1 is to 3 is to 5. That must be the corresponding ratio. Look at the options once again. Second option is exactly the same. It is given 1 is to 3 is to 5. Therefore, we can just take the answer for this particular question as B. That is the concept of problem number 4. Only thing you should understand from this model is the moment there are concentric shells like induction takes place, due to charge induction, this is plus q1 means this side it will be minus q1, this side it will be plus q1 again. In that induction process, q1 plus q2 will be the total charge on the second shell, q1 plus q2 plus q3 will be the total charge over the surface of the third shell. If a fourth shell is there, you can think of directly the charge on that fourth shell as q1 plus q2 plus q3 plus q4. This is the concept by means of which we people have solved this model question. 1 is to 3 is to 5. The correct option is B for this problem number 4. Let us check the next number, problem 5. Once again a model based on linear charge density, but the object considered over here is slightly different. The linear charge density of a uniform semicircular wire varies with theta as shown in the figure as lambda is equal to lambda naught cos theta. If capital R is radius of the loop, the charge on the wire will be how much? Once again 4 different options are mentioned. First option is lambda naught R. Second option is 3 lambda naught R. Third option is 2 lambda naught R by 3. And fourth option is simply 2 lambda naught R. Correct option for this one is the fourth option, that is 2 lambda naught R. But carefully first of all observe what are the values given. He said lambda, that is linear charge density, is varying with respect to theta in this form. So lambda is lambda not cos theta. That's what has been given there. And it is said over here, this is a semicircular uniform wire. Remember that one. Then you can definitely understand this now becomes the diameter of it. And we can all understand this now gives you the radius of that. And the semicircular wire is given this way. It is having positive charge on its surface entirely like this. It is given in the problem itself. Now in this case, let us take a small element over here. That element, you consider its length as dl. And at the same time you can understand, since the distance gap between these 2 points is taken very small like dl, this angle also we can take this one as d theta. And you can certainly understand this angle that is given in the problem as theta. This is only a small element of length dl, which is making an angle with respect to the center, that as a d theta. That is what has been given in the figure itself. First and foremost, if you look at this case, what is this linear charge density first? Let us write once again, linear charge density. That linear charge density is dq by dl. Charge per unit length, already we have discussed one model like this, but we have considered earlier a rod of uniform cross-sectional area. Now it is given in terms of a wire which is semicircular by shape. Now the concept here is, what is this dl? You can certainly understand dl can now be taken as r d theta. If I consider this OAB like, for example, this like a sector, then you can definitely understand this dl is going to be r d theta. Now I can cross multiply this one to write dq is equal to lambda r d theta. But it is very clearly mentioned in the problem, lambda is varying with theta according to this relation. So what we should write in place of lambda now? Lambda can be written lambda naught cos theta into r d theta. Now rearrange the system. You can directly write dq is equal to lambda naught r into cos theta d theta. Once again, when I just want the value of charge on the entire system, I should integrate that one. But integration to be made towards this between what? Minus pi by 2 to plus pi by 2. From this end to that end. That is what actually we people have to take up. Now look at this, can be now q is equal to lambda naught r cos theta d theta. That of course integral cos theta now becomes simply sin theta. Minus pi by 2 to plus pi by 2. You can all understand well, when I substitute the upper limit here, sin pi by 2 becomes 1. Minus sin minus pi by 2. Minus of minus 1 again is plus 1. So what will now be the total value? It should be 2 times lambda naught r. That must be the correct answer for us. If you just look at all the 4 options, 4th option is exactly coinciding with it. So 2 lambda naught r is going to be the charge on the entire wire which is made to form a semicircle over here. So correct answer for this particular problem, that is now going to be D according to the given options. Only thing you should understand here is, since it is a wire, that too it has got uniform distribution of charge because of its perfect shape. You just can take integration in between minus pi by 2 to plus pi by 2 to get the total charge on the entire system as Q as such. So what will be Q here? It is 2 lambda naught R, which coincides with the fourth option as given in the problem as such. So correct option for this one is D. This is problem number 5 what we have. Now let us switch over to question 6. That is the sixth problem we are dealing with. A uniform charged thin spherical shell of radius r carries uniform surface charge density of sigma per unit area. It is made of two hemispherical shells held together by pressing them with a force F as shown. Then what is this F proportional to? So then F is proportional to what? That is a concept. Of course, he has given the four options once again. First option is 1 by epsilon naught sigma square r square. And second one, 1 by epsilon naught sigma square r. Third option, 1 by epsilon naught sigma square by r. And fourth option, 1 by epsilon naught sigma square divided by r square. The correct option for this problem is the very first one. That's 1 by epsilon naught sigma square r square. That is the concept. What exactly is the case here? Let us see. He has just given us a figure. This is actually a complete spherical shell. This is the diameter of it. So according to the problem given, there are two hemispherical shells like. They are now pressed one against the other with forces like F each. What is this amount of force? He is asking you to calculate. That means two hemispherical shells like this, they are now held together this way by applying force on both the sides. That force over here is given F, this side also is given F. That means equal force is acting on either sides of this hemispherical shell like. That is the concept. Now what is this question? What is this F proportional to? That is the concept. But in true sense, whenever we talk about this force like, in terms of surface charge density, we people have to take up. What is surface charge density? That is charge per unit surface area. You can understand that. But in this particular case, we know well what is electric force per unit area. What is that electric force? It is half epsilon naught E square. There is a formula like this, all of you must have got this idea. That electric force per unit area is half epsilon naught into E square. But what is E over here? E is the electric field strength or the intensity of electric field. But all of us, we can understand well, electric field intensity is sigma by 2 epsilon naught. That is also the formula what we know. So what can we write now in this case? Write this value here. You will be getting now F is equal to half of epsilon naught into sigma square by 4 epsilon naught square. But you can certainly understand epsilon naught getting cancelled. You are left with half into sigma square by 4 epsilon naught like this. Till that extent we people can understand what is the concept there. But if you look at carefully, this is the electric force per unit area. But he says both are just being pressed one against the other. Then observe carefully what is the effective area of that face, which of course is in contact with the other. If you take one hemispherical shell, is it not the area we people used to consider? So what is this area now to be called? This is area of a circle. So what we can write now? Since the effective area is pi r square. What is that pi r square here? R is nothing other than the radius. Since it is a circular by shape, pi r square is supposed to be taken as the effective area. So what can we write now? Therefore, what will now become to the force? It is half of sigma square by 4 epsilon naught into pi r square. That is the concept. What for it is pi r square, you can now guess. Per unit area, this is the force. For the effective area pi r square, what will be the corresponding force there? So we can understand now, this can be rewritten like, right, F is now proportional to sigma square is there, r square is there, by epsilon naught is there. So what can we write now? It should be proportional to sigma square, r square by epsilon naught. Look at those options given over there, please. What are the 4 different options mentioned? One is 1 by epsilon naught sigma square r square. In fact, the very first option, that is in coincidence with this particular equation. So what can we write now? The correct answer for this particular problem is the very first option, that is A itself. So just to think of once again, in brief I will give you what are the formulae I have used. The very first concept is the electric force per unit area that's acting. It is half epsilon naught E square, where E is intensity of electric field. And that E we people have written in terms of sigma, and we people have straight away taken up the total effective area which is in contact over there, that is pi r square, since it is a circular one. Then for pi r square, what is the effective force? That's what we just want. So this is the idea of taking up this particular model problem, that is problem number 6, right? So the option for this one is A, that is question number 6 for us.